Hello everyone, my name is Antti Tölli. I'm a professor of wireless communication, signal processing here at CWC of University of Oulu. And today I'll give a talk on low resolution ADCs for extra large or massive MIMO, aiming to find a balance between performance, complexity and energy efficiency. And this is a joint work with few students, doctoral students of mine and senior members of the team and colleagues, specifically Professor Italo Acceni. Okay. So, in this talk I will cover aspects related to massive MIMO or extreme or extra large MIMO implementation, and specifically focus on low granularity ADC implementation, and specifically focusing on 1-bit ADC, 1 bit for both I and Q branches. Why do we need massive or extra large MIMO to begin with? So we're continuously going towards higher frequencies. Path loss is therefore increasing, and to cover the increased path loss, the typical approach is to increase the number of antennas. Basically, if we keep the size of the antenna array fixed, when we go into higher frequencies, the wavelength decreases, and therefore we can pack more antennas within the same space. And therefore, we are able to maintain the coverage up to a degree. And at the same time, when we increase the number of antennas, the spatial degrees of freedom increase, and we are able to serve simultaneously more users. And at the same time, when we go into high frequencies, we have more bandwidth available. On the other hand, when we have higher bandwidth, the available power needs to be spread over the bandwidth. Therefore, the power density decreases, and again, we need to have large antenna arrays to be able to do beamforming and focus the transmitted power towards the served users. So, why we would like to have fully digital architecture for massive MIMO? Again, beamforming is required. And if you look at some existing implementations, for example, focusing on millimeter wave frequencies, a typical approach, to my understanding, seems to be relying on hybrid architectures, that we have a limited number of RF and baseband chains, and the beamforming or the antenna arrays or combining over antennas is partially carried out in the analog domain. So we have an analog circuitry that we need to tune together with the digital combiners across the RF chains. The downside of this is that, first of all, the channel estimation becomes difficult. We need to do some scanning across varying these analog weights that would be focusing the to receive all transmitted power towards certain directions, and therefore the training overhead increases accordingly. And at the same time, of course, the spatial degrees of freedom are limited by the number of RF and baseband chains that we are equipped with. Now, the ideal case is to equip every antenna with a dedicated RF and baseband and a dedicated ADC chain for both I and Q, but the complexity and the cost and the power consumption is increased when increasing the number of antennas. So the traditional solution is to use high for massive MIMO, for the lower frequencies at least, is to use ADCs with some number of bits in terms of parameter Q assigned to each ADC converter for both I and Q. And now the ADC power consumption in general can be shown to scale exponentially with respect to the number of bits that are used to quantize every antenna output, so 2 to the power Q. And at the same time, the data exchange, if you think about the distributed architecture, we have some centralized entity connected to remote radio heads, and then we have some front haul communication, front haul links between the centralized entities and RAH. The data that is required to be communicated over this front haul scales with number of quantization bits as well. Now, in the extreme case, when we set Q to 1, we go down to 1-bit analog to digital converters. This is the simplest, cheapest the least power consuming data conversion device that we can come up with. And mathematically you can express this as a sine function. So you can see that in the right hand side in the figure 3, input-output characteristics for an ideal 1-bit ADC. And this at the same time can greatly simplify the RF design, and for the analysis, which we will cover a bit more detail later on, the analysis also gets much simpler for the 1-bit ADC case compared to the higher order quantization cases due to this simple sine function. Also at the same time, the performance degradation due to 1-bit quantization can be fairly modest. Now let's spend some time on explaining the basic principles why 1-bit ADC works to begin with. The signal recovery heavily relies on stochastic resonance, the importance of having an appropriate amount of noise introduced at each antenna branch. So in the left-hand side, we can see two constellation points, P1 and P2, right? They are plotted in the left-hand side figure with a circle and cross, blue and red. And now after 1-bit quantization, so due to this very coarse quantization, the output of the 1-bit quantizer when applied to both I and Q can get only 4 discrete values. 1 plus j, 1 minus j, minus 1 plus j, and minus 1 minus j, right? So in this particular example, when we apply the 1-bit quantization to these noiseless constellation points, they are both rounded to the same point, 1 plus j, okay? And therefore, after quantization, it's not possible to distinguish between these two constellation points. Okay, so this is the case without noise, and only with a single sample, okay, single antenna, okay? Now, if we have n antennas, n can be large, let's say hundreds, and we take independent samples from the transmitted constellation points. So this basic example is a Gaussian channel, so you can imagine that channel is all ones vector, the simplest possible case. And now if there's no noise, every antenna will get the same quantization output, 1 plus j. Okay. But now when we add noise, let's assume that on the right hand side, now we add independent noise sample, where the noise samples are drawn from a complex Gaussian distribution with zero mean, variance 1. So the variance here is not optimized, it's just add on. So you can now see that when we plot these noisy versions of transmitted constellations P1 and P2, the right hand side scatter plot, you can see that both red and blue noisy versions of transmitted constellation points form a kind of a cloud around the transmitted constellation points. So you can see that if you look at the red constellation points, the mean which corresponds to 1 plus j, then we add this noise at the receiver. You can see most of the noisy samples are located in the upper right hand part of the plot. And then you have a few samples that all those points are at the output of the 1-bit quantizer, they are rounded to 0.1 plus j. But then there are a few antenna samples that are also crossing to other quadrants of this plot, like to the upper left corner and right lower corner. So now when we take the mean of all these samples, we get the red cross. This is actually the mean. This would be the estimated constellation point at the output of the receive combiner. And since the channel here is very simple, all ones, the match filter combiner is also all ones combiner. So basically we are just summing up the noisy versions of these transmitted constellation points. And at the same time, when we look at the blue constellation point, which corresponds to the 0.5 scaled version of the red one, then you can see that we have much more crossings to other quadrants compared to the red one. So when we take the mean of all these samples across antennas, basically applying the ideal match filter here, you can see that the mean is clearly distinguishable from the red one. So the blue cross is clearly distinguishable from the red cross. So this is the basic principle why 1-bit ADC works. It's a combination of having a large number of samples aggregated from large number of antennas, each with sufficient amount of noise at the receiver. So again, if we don't have any noise, if the noise is very small, then all those samples would be concentrating very close to these transmitted signals, and we would not be able to distinguish between these transmitted constellation points. So having a proper amount of noise introduced at the receiver is very important. And now let's have a look at the channel estimation with 1-bit ADCs. Now this is with a fading channel. And we can see that some results that have been published in a couple of journal papers that are cited in the footnote. First of all, we can see that the pilot sequence is very important. The proper selection of a pilot sequence is important for channel estimation. So we have here 4 different channel pilot sequences used for channel estimation. This is a single antenna case. The pilot sequence length is 17, and we have, let's say, 4 different sequences. One corresponds to Chadov-2 sequence, commonly used in 5G. Now, the other one is a DFT. I believe this corresponds to the second column of the DFT matrix. Then we have all ones vector, that's indicated with the red circle, and then we have the optimal sequence given the 17 length pilot sequence. Now, also on the right hand side, we have the corresponding performance, MSE performance for the channel estimation. Now, for the optimal and the worst case, which is the all ones vector used for the channel estimation. And you can see that in both cases, when we are in the low SNR region, let's say below 0 dB SNR, the sequence does not really matter. We are dominated by the noise, Gaussian noise introduced at the receiver. But when we go beyond 0 dB in this particular example, the noise contribution decreases, but now the quantization distortion starts to increase. So it's very important to find a proper amount of noise introduced to the receiver to remain in this sweet spot, which in this particular case happens to be around 0 dB SNR. Okay. Now the optimal pilot sequence that we assign actually can recover because the pilot is now evenly distributed within this unit circle, so it can actually recover after combining dispreading with the pilot sequence. It can actually recover the phase accuracy for the channel estimation, but it cannot recover the amplitude without a proper noise added at the receiver. So the difference here is basically explained by the higher accuracy for the phase estimation provided by the optimal sequence. This assumes a single user estimation, assuming a linear LS estimate. In general, we can use linear or Busgang MMSC type estimator, but in general, the BLMMSC, Busgang linear MMSC estimator, is not optimal, shown in very recent publication. You can get some modest gains using some nonlinear structures. But the linear is close to good enough in general, if we have large number of antennas and large enough number of pilot symbols available. Okay, so let's have a look at the data detection performance with 1-bit ADCs. So here we in general consider a multi-user scenario where we have k users, each transmitting a symbol from a constellation alphabet with some number of symbols, for example 16 QAM. And then, since we are working in the multi-user MIMO uplink, each user channel is described by a vector of size m. And now we have k users accessing the base station at the same time. So the superposition signal at the receiver, which is y, can be expressed as the simple matrix equation in equation number 1. So we have a superposition of all transmitted signals x traversing through the user-specific channels, and then we add independent AWGN noise at the receiver. And then we apply quantization. Each antenna output, y, and this q here is a sine function for both I and q branches of the received signal. So for each antenna output, we can think that we have one point drawn from the QPSK type constellation. Then in order to detect the data as a symbol, we need to combine all these parallel samples across antennas. And this combiner is given by this V matrix. So we have a user-specific combiner with dimension m. So the total size is m by k. Okay. So data detection process maps each the estimate x hat sub k to one of these possible data symbols in S, the transmit constellation, using, for example, nearest neighbor decoding. One important aspect is that we can actually, given data symbol vector x and the known pilot sequences, we can actually compute the expected values for each transmitted symbol in closed form. You can see, if you go back to the previous example, we can see that due to one-bit quantization, even though we can get close to the original constellation, there's some remaining distortion, especially in the amplitude domain, that causes distortion of the original transmitted constellation composer. So now we can take into account the impact of the one-bit ADC, the pilot, SNR, and so forth, to compute in closed form, assuming a maximum ratio combiner in this case, what is the expected value for each transmitted constellation point. You may ignore the math here and find the details in the publication if you are interested, but we can have a look at an example, what happens to the constellation point and the expected values in different regions of SNR. So here we have a 16 QAM transmitted constellation, and we have 128 antennas at the base station, and we have corresponding received constellation, let's say clouds corresponding to each transmitted constellations for 3 different SNR values, 0 dB, 10 dB, and 20 dB. You can see that at 0 dB SNR, the clouds are more or less distinguishable, right? So there's some crossing from one cloud to another, causing some error, but mostly the transmitted or received constellation points are concentrated around the mean values, the expected values that are now computed in the closed form. Okay. Now, when the SNR increases, you can see that the cloud size decreases, since we have pretty good phase. Let's say we can distinguish in the phase domain the different transmitted or received constellation clouds. But since due to the lack of noise, we lose the amplitude resolution, and you can see that those points that have the same phase but different amplitude, they start getting close to each other. And in the high SNR, 20 dB SNR, it's not possible anymore to distinguish between points that have the same phase. So they are completely overlapping. So this will cause an error floor. And this is actually shown here in the SER plot with respect to SNR. You can see that we have the left-hand side, we have the ideal case with perfect quantization, no impact on the pilot sequence. On the right-hand side, we have the SER simple error rate with 1-bit quantizer. And again, you can see that there's this sweet spot somewhere around 5 decibels SNR that gives the lowest SER. Again, just like in the channel estimation, the left-hand side is in the noise-limited region, thermal noise-limited region. And then at the right-hand side, we are in the quantization noise-dominant region. So in order to stay within the sweet spot, we need to have a proper power control. So we have this non-monotonic behavior of the SER with respect to SNR, so a traditional power control algorithm does not really work. So we have actually a very simple idea that we actually worked together with Nokia earlier to take into account the non-monotonicity behavior of the power control and try to find a power allocation in a dynamic setting where we stay close to this sweet spot. So the simple idea here is to reuse the pilot symbols to capture the non-monotonicity of the data detection performance. So we use the pilots here, Sadovcu sequences, let's say sorted Sadovcu sequences to mimic data with 2-level modulation. So we can assume that we have a Sadovcu sequence P multiplied with a certain power, and then we have the same sequence multiplied with the higher power. So when we plot this in the diagram, we can see that we have 2 circles with different diameters, okay? So now, depending on the SNR, and assuming that we have the pilots can be now, because we know the pilot sequences, we can, at the output of the combiner, we can actually compute that how far would be, given the combiner, how far would be this estimated pilot data symbol to be from the original constellation point. So you can see that in the left-hand side, we are heavily noise limited. So we have quite a random figure. Then in the right-hand side, we have no noise. So basically we cannot distinguish anymore between the different amplitudes. But somewhere around -2 decibels, we have a proper amount of noise introduced. And now you can see that we can distinguish between these two set of symbols. So this we can use to mimic a higher order modulation to find a noise level that would provide also good performance for the actual data detection. So this is the simple MSC metric that we use for the evaluation. So we have the Q here, it's the known sequence, and then we have the R, which is the sample matrix, and then we can use the sample matrix directly to compute the match filter receiver, and then we can compare an estimated symbols Q and the known symbols Q to find a power allocation that would minimize the MSE. And now, since we are at the power control phase, we can only measure the MSE of the pilot sequences, and that is actually shown here in the left-hand side figure. Again, we have the AWGN dominated region on the left, and then quantization distortion dominated region on the right-hand side. And we can map this MSE to the actual simple error rate of the data detection SER. And then both of them have the same similar sweet spot behavior, but we can experimentally find a delta that we should apply to tune the power based on MSC to have a proper mapping to the data detection SER. The power control is fairly simple. It consists of what we call differential power control. So we send 3 shorter Zarovtsu sequences with different power levels, and then we can form 2 pairs of, let's say, these aggregated pilot sequences, and then can form these 2 scatter plots and compute the MSC for both options. And then we can use this to identify whether we are in the quantization dominated region or on the noise dominated region. If we only measure the MSE with the 2 levels, we don't know really whether we are on the right-hand side or left-hand side. So we don't know whether we should be going down or up to improve the SER. But having this differential approach, we can see now that, okay, which one is smaller. If the left-hand side is smaller than the right-hand side, we know that, okay, we should be decreasing the power, and vice versa. Okay, there's just a simple example how this SER behaves with respect to so we have a single user here in a dynamic setting moving around, and the path loss is changing. And you can say that if you have a fixed power, the SER changes with respect to time, but it's not close to the target SER value, which is somewhere below 10 to the -4. And then we have the traditional case, which does not take into account the non-monotonicity. You can say that now, once we end up to the quantization-dominated region, it tries to increase the power all the time, right? Because it assumes monotonical behavior of the SER, and therefore we just get deeper and deeper into the quantization-dominated region, while the proposed algorithm obviously is able to stay within the target SER. Now, an interesting extension of the single-user case that we covered earlier is the extension to multi-user case. Okay, so far we considered the data detection for a single user. Now we consider detection of multiple users at the same time. Okay, the main difference here is that the expected values of the soft estimated symbols still depend on the pilot matrix and the transmit SNR, just like in the single user case, but they also depend on the specific data symbols transmitted by the interfering UEs. Okay, so I try to explain this with this example that we have 2-user scenario. We have user 1 on the left-hand side. Let's say the expected values of the transmitted 16 QAM constellation plotted for user 1 on the left-hand side. Okay, so the green constellation illustrates the 16 QAM transmit constellation, and then the scatter plot on the left-hand side shows the dependence of the data symbols 1 and 2. So depending on what is the data symbol transmitted by UE2 that would be now interfering the reception or detection of UE1, the expected point changes, right? So the blue ones correspond to the inner circle. So you can see actually that we have 3 different expected points for each transmitted data symbol of UE1, depending on what was the data symbol transmitted by the UE2. And this depends only on the amplitude of the transmitted constellation of UE2. So you can see that in 16 QAM we have 3 different amplitude levels: inner, the mid circle, and the outer circle. Okay, and all those 4 points, for example the red one, the outer circle correspond to one point in this expected cloud of points. Okay, so now we can use this for joint detection. If we know something about the other user, it can improve the distinction of the transmitted data symbol of the other user. In general, we can say that conditioning reduces uncertainty. Okay, so the left-hand side is with 0 dB. Again, with the right-hand side, we have a high SNR and the lack of noise. So we can see that now the constellation points start to overlap, and therefore it's difficult to distinguish. But with this additional interdependency of the transmitted symbols, we can now still detect those transmitted symbols better than when we ignore this interdependency. So here we have a plot for 2 users, 120 antennas, 31 length pilot sequence, and we can compare the joint detection performance. So joint detection here takes these interdependent expected values of the soft estimated symbols of interfering UEs into account interdetection. So detection is, in this particular case here, it's a simple maximum likelihood search that we look at the, or exhaustive search, okay, not maximum likelihood. It's an exhaustive search over all possible combination of transmit symbols, and then it compares that to the estimated at the output of the combiner. This is the x hat, is the vector of estimated the soft symbols for users 1 and 2, and then we try all different combinations of transmit symbols for both user 1 and 2 and choose a pair of symbols that results the smallest least square error between this, the smallest joint distance between the estimated and the hypothesis. Okay, of course the complexity grows exponentially, but we can apply kind of square detection type ideas to reduce the complexity greatly. And you can see that from the plot that compared to the black one, which is the single user detection, the detection performance can be improved greatly by 2 degrees of magnitude by applying the joint detection. Okay, the final topic, I will briefly discuss 1-bit ADC implementation in the distributed MIMO with remote radio heads connected to a central unit. So now we have each remote radio head equipped with multiple antennas, and each antenna quantized with 1-bit ADCs. The extension to the single cell case that we covered earlier is simple. Basically, we just add subindex B to the received signal vector Y, and this Y sub B is now specific to a certain base station or remote radio head B. And then the output of this 1-bit ADCs is applied individually to each antenna, so the extension from the single cell to multi-cell is fairly straightforward. Now, in order to be able to do the analysis, we need to apply a transformation to this highly nonlinear quantization function Q. Okay, if you recall, that's just a step function. So you use so-called busking decomposition to decompose the received quantized vector R into a linear version of the input signal plus a uncorrelated quantization distortion component. And the good thing with 1-bit ADC is that we can compute, in many cases, this Buscan gain matrix A and the statistics of the quantization distortion in a closed form. Okay, and this is something we can utilize later on. So now with this model, when we apply now a combiner across all these distributed antenna heads, we can form an estimate of the transmitted signal dk, that's d hat sub k. And now when we split the received signal into different terms, we can see that we have the desired term, then we have the inter-user interference, then we have the noise, and finally the quantization error. And then given these terms, we can actually form so-called signal to interference noise distortion ratio, where we have the desired term in the numerator and then all these unwanted terms, interference, noise, and the quantization in the denominator. We can see that this covariance of the noise depends on the noise levels introduced at each base station. This is an important factor that we can play with later on, in addition to the transmit power, which is indicated by rho k here. And as I mentioned, due to the 1-bit operation, these covariance matrices can be computed fairly straightforwardly using this arcsine law. Now, just a couple of examples. What happens with the SNDR? Now this is a single user case. First, what happens with the signal to noise distortion ratio when we have very simple case, 2 remote radio heads serving a single user. Okay, now we have remote radio head 1 located at 0 meters, remote radio head 2 located at 100 meters. Okay, and the user is moving from remote radio head 1 to remote radio head 2, so it moves 100 meters. Now we have 3 different transmit power levels shown here for the UE, okay, -5 dm, 7.5 and 20 dBm, okay. The black curve here shows the lowest power, and we can say that when we are close to the base station, we have the highest SNDR, and then we get further away from the neither of the base stations, the SNDR drops close to 0. Okay, so we are in the noise-dominated region. Now, when we increase the transmit power, the user, when we are close to the base station, the noise is actually dominated by the quantization. So with fixed power going away from the base station actually increases the SNDR because the quantization is reduced. It increases up to a point, 25 meters here, and then it enters the noise-dominated region, okay, and so forth. And then we increase it further, and you can see that we are always in the quantization-dominated region. Okay, so what can we do here? Now we have this power, okay, we can adjust the power, but now we can also play with the noise level introduced at each base station. So let's imagine that again we have the same scenario, 2 remote radio heads, but now we have user located in different points at the base station in the network. Okay, we have 2 locations, 10 meters and 50 meters. For example, interesting case is when we have user close to remote radio head 1 and we start increasing the power. So first we are in the noise limited region, the power, the SDNDR keeps increasing, and now the remote radio head 1 enters to the quantization dominated region, so the SNDR starts to decrease, okay? But then we increase it further, and now we can reach also the remote radio head 2, so the total SNDR starts to increase, okay? And that's why we have this non-monotonic, non-unimodal behavior of the SNDR. Now if we allow at the same time to adjust the noise level at the remote radio head 1, when we start increasing the power beyond 0 dB SNR, we actually start increasing the noise at remote radio head 1 with the same ratio. So it remains at the sweet spot, and therefore the combined SNDR actually can be improved further. So that's the importance of proper amount of dithering, or including the proper amount of noise at the receiver. Okay, so then we can form power and joint power and dithering level optimization. But due to the time constraint, I might skip most of the details. But in general, if you look at the max-min SINDR problem that is shown in the lower part of the slide, you can see that the SINDR, which the expression was given in the previous slide, depends on 2 optimization variables. It depends on the transmit power at the UE and the dithering or noise level introduced at each base station or remote radio head. And obviously the dithering level is lower bounded by the AWGN introduced by the RF, but we can actually start adding some artificial noise on top of that if it's needed. And a couple of examples showing the potential gain when we do the both joint and the joint power, transmit power and the dithering level optimization. You can get significant gain in the max-min SINDR values when we do this in an appropriate manner. Okay, so this concludes my talk, and there are several papers published recently that cover more details if you are interested in this topic. Thank you for your attention, and would like to get some feedback if you have any. Thank you.